I'd like to look and see where we are in the problem of how does one classify all finite groups. We made quite a bit of progress pretty easily in the last handout when we were able to classify all groups of prime order. We saw that amongst all groups of a given prime order P, there is only one isomorphism type, and that's Z mod P. A group of prime order P has to be cyclic, and there's a unique cyclic group of any given size, and so there you go. So now I want to keep pushing this question further and see what we know. So let's suppose that G is a finite group with n elements. If n is 1, then of course G has only the identity element in it, and all groups of order 1 are clearly isomorphic to each other. They have the same structure. And so there is only one class. So amongst all groups of order 1, there's obviously only one class, and the model is any trivial group that you like. Okay, if you like, you can just take it to be 0, with 0 plus 0 being 0, the only possible operation. Okay. What if your group has order 2? What if G has 2 elements? Well, 2 is a prime, and as we just saw in the last handout, that forces G to be isomorphic to Z mod 2, so there's only one class. So amongst groups of order 2, there's only one isomorphism type, and that's the type Z mod 2. There's the model. Of course, order 3 is the same story because 3 is a prime. So amongst groups of order 3, there's only one class, and that's represented by Z mod 3. Please note so far they're all cyclic. And so the natural question is, well, gosh, what about order 4? Of course, 4 is not a prime, so whatever we do here is going to be different. So I want us to start thinking about how could we classify groups of order 4. This has the potential to be more interesting than order 2 or order 3. So let's start thinking about what we know about groups of order 4. Certainly there is the trusty cyclic group Z mod 4, right? But is there anything else? Right? So start thinking about the groups that we've looked at this semester and think about all the groups of order 4, and were any of them different from Z mod 4? Were any of them not cyclic? Well, we've talked about the Klein 4 group, and it's come up multiple different times. We originally saw it, I believe, as the subgroup R0, R180, FV, and FH inside of the group D4. Okay, but I have also talked in class about the group Z2 cross Z2, and I've called it the Klein 4 group too. So I've called these these two different groups here, I've called them the same thing for some reason. Well, as you might guess, they are isomorphic to each other. Z2 cross Z2 is isomorphic to this subgroup of D4, and so that's why I don't mind calling them the same thing, because they are algebraically the same anyway. So so far, it looks like we have two candidates. There are two candidates for groups of order 4, a Z4 and the Klein 4 group, which I'll take to be Z2 cross Z2 for the remainder of this discussion. But there's some questions, right? One question would be, are these two actually different? Maybe they're the same isomorphism class. Maybe Z4 is isomorphic to Z2 cross Z2, and therefore they're really not different. They're the same. The bigger question is, this is hard sometimes. Am I missing anybody? Is there a third isomorphism type amongst groups of order 4 that's not captured by one of these two? Am I missing someone? So let's look at the first question first. Are these two groups actually different? Is Z4 perhaps isomorphic to Z2 cross Z2, or are they different? We hope they're different. And for the first question, the answer is yes, they are different, and it's easy to see why. Right? It's easy to see that Z4 and Z2 cross Z2 are not isomorphic to each other. Here's why. Well, suppose to the contrary that they were isomorphic. Well, then Z2 cross Z2, being isomorphic to a cyclic group, must itself be cyclic. And notice I'm using an invariant here. I'm using the fact that being cyclic is an invariant. But you can check that every element of Z2 cross Z2 has order 1 or 2. So it's not possible for it to be cyclic. For this to be cyclic, it would need an element of order 4, but it doesn't have any. And so there's no way that Z2 cross Z2 can be cyclic, and therefore it's no way that it can be isomorphic to Z4, because being cyclic is an invariant. So yes, they are different. But the bigger question is one of completeness. Did I miss anybody? These are two different isomorphism types. Is there a third type I didn't know about? In other words, if G is any group of order 4, no matter what it is, pull it out of a hat at random, must G be isomorphic to either one of these two? And again, the answer is yes, but this takes some argument. So what I want to do here is I want to map out the argument. I'm not going to do it all because you can read it yourself, and lots of it is straightforward, but I do want to show you the way this gets argued, right? So I want to show that I have actually successfully classified all cyclic groups of order, all groups of order 4, by two types, Z4 and Z2 cross Z2. Okay, so that's my theorem. Theorem 1. If G is a group of order 4, then either G is Z4 or G is Z2 cross Z2. And that tells me that I've got everybody, because if you take any group ever, it's got to be isomorphic to one of those two. Moreover, these two are different from each other, so I have completely classified groups of order 4 as soon as I prove that theorem. Let's prove the theorem. The proof is neat. But notice that this proof can get a little bit sticky sometimes, and please appreciate we are only talking about groups of order 4. This gets way, way harder the bigger your groups get, and it's already kind of hard just with a group of size 4, just really small. Okay, so the proof comes in two cases. The two cases are, well, either G is cyclic or it's not. Okay, so let's walk through the proof. I'm going to give you sort of the outline of the proof, and I think what are 5 steps. Yes, a 5-step proof. I'm going to give you the outline of the proof and let you read how the details get filled in. Okay, so step 1, let G be a group of order 4. All right, here's the first case. If G is cyclic, it must be isomorphic to Z4. Well, we already know that. Okay, so if the group is cyclic, that is going to take care of this clause of the theorem, and what I've got left is handling this one. Okay, so, but again, my group is either cyclic or it's not. So in the cyclic case, I'm done at Z4. What I got to argue is that if G is not cyclic, it has to be Z2 cross Z2, and that's what the rest of this proof does. Okay, so step 2. Suppose now that G is not cyclic, and that G has 4 elements, call them E, A, B, and C, where of course E will be our identity. The first step in this is to determine the orders of all the elements in G and then use that to map out the KV table. And I'm going to let you do this, okay? So you can read this, and we're going to use things like Lagrange's theorem. This might sound an awful lot like a homework problem you just did. We're going to argue that every element in the group has order 2 or 1, and so that means that everybody squares the identity. So your group was EABC with E the identity. But then you argue here by Lagrange's theorem that everybody has to square to the identity. Every element squares to the identity. So there must be identities along the diagonal. And then what I want you to do in the Canvas quiz is to map out the rest of the table. So in the Canvas quiz, I ask you for all the other entries. There are 6 missing entries. I want you to find those entries and do the Canvas quiz. All right, and you'll need that table for the rest of the proof. Right. So step 3 is I am going to start building an isomorphism between this group G and Z2 cross Z2. And the way I'm going to do it is I want to sit down. I'm actually going to build it for you. So you're going to have 4 elements in your group G, E, A, B, and C. E, A, B, and C. And I'm going to map them to Z2 cross Z2 in this way. So here are the 4 elements of Z2 cross Z2. And let that be your function. That's certainly a good function. And you need to check that it's a bijection. So you check that this function right here is a bijection from G to Z2 cross Z2, and it is. Okay? Now you move on to checking that alpha so defined is actually a homomorphism, right? Which means you got to prove that alpha of x and y operated in G is the same thing as alpha x operated with alpha y in Z2 cross Z2, and in Z2 cross Z2 the operation is called a plus. So I got to show that alpha of xy is alpha x plus alpha y, where this plus is plus in Z2 cross Z2. Okay? This is not too bad, to be honest, but you have to do it in 4 annoying cases. Okay? Oops, I guess it's 3 cases. Yeah, just 3 cases. There are 3 cases here, and you got to check it in 3 cases. And you can do it. It's not hard. I'll let you read it, but it's a little annoying. And again, appreciate this is annoying, and we're only talking about a group of order 4. At that point, we're done. I'm going to argue that alpha is a homomorphism, but we've also already argued that it's a bijection, so alpha is an iso. And now we're done with the theorem. If G is cyclic, it's Z4. If G is not cyclic, then the argument above produces a map, alpha. And that map, alpha, I've just proven is an isomorphism from G to Z2 cross Z2. And we're finished, right? Thus, we have succeeded in classifying all groups of order 4, and it only took us 9 minutes. Okay, so we have classified all groups of order 4. There's only 2 isomorphism types, and the models are Z4 is one and Z2 cross Z2 is the other. So now we can fill out our classification table for groups of order 4. There are only 2 types up to isomorphism, and the 2 types are Z4 versus Z2 cross Z2. So we can extend our classification of finite groups a bit further, especially once we realize 5 is a prime. So 5 is a prime, so there's only one class, and it's got to be model Z mod 5. Right? And of course, you can't help but ask what happens next with order 6. Okay? It is surprisingly hard to prove. If we get time this semester, we'll get into it. If not, we'll save it for the fall. But these are really good questions to ask. Is what else can you say about classifying finite groups based on their order?